So thank you very much. It's a great pleasure to be here. And I know the series is Bose-Einstein condensates. We will get there, hopefully. But a lot of what I will talk about draws upon the early work in the BEC field and what we've learned on how to control atoms. And as Michael says, the thrust is that two atoms are better than one, and we can actually form molecules with atoms. Okay, so the talk is really going to be focused on molecular physics. So why would we want to use ultra-cold molecules? So there are four key areas of modern science that use molecules. The first and very important one is precision measurement and tests of fundamental physics. And there the interactions and the symmetries in molecules make these measurements sensitive to physics that is inaccessible to atoms. And these kind of measurements, such as this electron EDM measurement using a molecule, thorium oxide, can now be competitive with particle physics experiments in terms of the mass and energy scales that they're probing through these sensitive measurements. There's also the area of ultra-cold chemistry. You know, the world around us is actually made up of molecules, and they interact and react. With ultra-cold systems, we can get fundamental insights into how chemistry works at a quantum level. And then there are the two topics which I'm sure you've probably heard a lot about in this series, which is namely quantum computation and quantum simulation, where I think molecules also have something interesting to offer, particularly in the realm of quantum simulation, which I hope to explain, where arrays of molecules with their strong dipolar interactions offer new opportunities. So why is it so rich? Well, this richness all stems from the internal structure of a molecule, right? Two atoms are better than one. As soon as we put two atoms together, we have their binding energy, the vibration degrees of freedom, rotational degrees of freedom, as well as the usual hyperfine and translational degrees of freedom, and this dipolar interaction. And this spans a huge range of energies, different scales. Mostly what we're concerned about in the ultra-cold world is accessing this rotational degree of freedom, okay, which is completely absent in atoms. And the rotational states of a molecule form this beautiful ladder. This ladder goes up and up and up. And all of these states are very long-lived. Okay, their radiative lifetimes are effectively infinite on the time scale of the experiment. And these states can be coupled with microwave fields, because there's a dipole moment in the molecule. And that means we can play games where we encode spins or qubits in the internal space of the molecule and use those to perform experiments. But I really want to emphasize it's not just a two-level encoding like this. You've got this whole ladder in which to play games. And in our experiments, we've driven up to the 6th rotational state, and that was really just limited by how many microwave fields we could apply to the experiment. And there are proposals to use this internal space as what's called a synthetic dimension. So you map the energy levels of the molecule onto sites in a lattice, and then you can engineer a kind of lattice problem entirely in the internal space of the molecule, where the tunnelings are set by microwave fields, which gives you a great deal of control. And then you just change your microwave fields and you can go to a different geometry without reconfiguring the experiment. I should point out, it will become evident in the talk, that each one of these states actually has hyperfine structure. For rubidium cesium, that corresponds to 32 states. And initially you look at this and think that, well, that's quite scary, and maybe it is. But I want to convince you that actually it's another resource. Okay, so the fact that we have these hyperfine states allows us to do different things, new things. So, for example, a few years ago, we demonstrated that by changing the magnetic field we can find a pair of hyperfine states that have exactly the same magnetic moment. And when we tune to that field, we can get exceptionally long coherence in encoding the information in this pair of hyperfine states. So that's an opportunity that comes with this hyperfine degree of freedom. The real selling point, I think, of ultracold molecules is this access to dipolar interactions. In fact, this is something that many people in the ultracold world crave in their experiments, and there are different ways of achieving it. In molecules, the dipolar interaction is very controllable. It can be either through the transition dipoles that I mentioned. So for example, if I put a molecule in n equals 0 next to a molecule in n equals 1, they're connected by a transition dipole, and that naturally leads to something called a spin exchange interaction, where the molecules can change place. We can also create fixed dipoles in the lab by adding electric fields to the experiment. And so this makes the system very tunable. And so a lot of the proposals have worked on the basis that if you could create arrays of molecules like this, then you would be able to engineer these interactions. And this then becomes a very complicated many-body system in which to probe new physics. And you can read more about the kind of experiments you can do in the realm of quantum computation and quantum simulation in this publication. The challenge really is molecules come with extra richness, but they also come with extra challenges in terms of controlling them, particularly their internal and external degrees of freedom. And that's largely what I'm going to talk about today. So let me just give you a glimpse of some of the challenges and some of the physics that one could think about exploring. And this is taken from this nice review from a few years ago. So the simplest scenario is we fix the molecules in an optical lattice, and then this is the range of physics, quantum magnetism type properties we could explore in this case, where it's the spins that are moving around in the lattice. But to do that, we need to control electric fields, we need to be able to prepare the molecules in the lattice, and ideally we'd like to be able to address them. And this is just the two-level physics. You could then introduce more levels in the molecule. Remember, we've got this whole internal space with which to play. And then you can engineer spin-orbit coupling. You can look at topological phases and Chern insulators, phenomena in condensed matter physics that then become accessible in this type of system. But we need, of course, better control with microwave fields to control the many states, and also the addressing becomes important. And then the real, what lots of people are aiming for, molecules have these long lifetimes, so why not let the molecules move around in the lattice? And then we get different kinds of models. TJ models are related to high temperature superconductivity, the topological superfluids and dipolar chains and clusters will form. But this requires efficient cooling to prepare the molecules in the lowest band of the lattice, and also control of collisions or chemistry, as we'll see. I should also mention that molecules are not the only system that give rise to dipolar interactions. Okay, we have highly magnetic atoms such as erbium and dysprosium, and I think you've heard talks on this already. But the molecular dipoles are about a factor of 1,000 stronger. And then we can go a factor of 1,000 stronger again to Rydberg systems, where the dipoles are huge, but the lifetimes are very short. And so in this kind of systems, you really have to think of the dipoles as being fixed, whereas molecules give you these strong interactions and mobile particles, which can push the physics into new regimes that are not accessible in the magnetic atoms. So it's a natural question to ask, well, how do you make ultracold polar molecules? And there are really two methods that have come to the fore over the last decade or so. One is direct laser cooling, Okay, so for a long time it was thought you wouldn't be able to laser cool a molecule. And the reason is laser cooling requires a closed optical transition to scatter many photons, which is why alkali atoms work so beautifully. They have that property. Molecules in general don't, except there is a class of molecules that do closely exhibit that. And so, whereas in the alkalis, you might need one repump laser, in a molecule, you can see you can get away with 2 or 3 repump lasers for a very specific class, such as strontium fluoride or calcium fluoride. I won't talk about this today. What I'm going to talk about is using all of the atomic tools that we've developed over the years to make cold atoms and then turn them into molecules. So associate those atoms into molecules. So the recipe is, as I said, we use the tools that we have to make ultra-cold atomic gases. And then we have a two-step process to make the molecule. The first is we use a Feshbach resonance, which, as Mikhail said at the beginning, I worked on many years ago in the early days of BEC. But now we use it not to control the interactions, but to actually convert atoms into molecules. The molecule we produce this way is actually very weakly bound, and so we transfer it to the ground state with lasers in a process called stimulated Raman adiabatic passage. And this removes the binding energy of the molecule, which is typically about a few thousand Kelvin. And this was first achieved in 2008. And now there are many experiments around the world working with these types of molecules. They're all bialkali molecules, using the fact that we can cool the alkali atoms exceptionally well and then make these molecules. Okay. So in my group, we actually have 3 experiments, and I'll tell you results from each of these through the course of this talk. The oldest is a simple bulk gas experiment. And more recently, we're working with optical tweezers and a microscope, all using rubidium cesium molecules, which we first produced in 2014. So the plan really today is to give you the full details of how we make molecules, then how we control the internal state, how we control the motional state, and if hopefully I will have time, we'll get on to how we control collisions. Okay. So let me begin with part 1, making molecules, and I'm going to give you a sort of tutorial, a simple tutorial on Feshbach resonances, magnetoassociation, and this transfer to the ground state. Okay. So I always like to start in explaining what a Feshbach resonance is with, first of all, what is a scattering length? So this is how I think about an ultracold atom. We have to think of it as a wave. So this you can say is the de Broglie wavelength of an atom at ultracold temperatures. And then if I put an atom at the origin, as this atom approaches, it feels the interatomic potential. Okay, this is the potential that supports bound states. And of course, it has to modify its wave function to respect this bound state, this interatomic potential. But what you notice at long range, there just seems to be a phase shift. Okay, it just looks like the wave has been phase shifted. And this is the scattering length, A, in this phase shift. It's sensitive to the depth of this potential, or how many bound states there are. And in the ultracold limit, we like to think of the collision cross-section as just being proportional to this scattering length squared. Okay. This picture is not quite accurate because the length scales don't fit on the diagram well. So if I draw it properly, actually the de Broglie wavelength is very long and the range of the potential is very short. And so it looks a bit more like this. And this would be a positive scattering length where you can see this phase shift. Now, if I imagine increasing the depth of the potential, then that modifies the wave function like this. And in this case, now you see this intercept is negative. So the scattering length can be negative. That's an important point. And if I keep increasing the depth of the potential, I add a bound state to the potential, which corresponds to adding another node in the wave function. So you can see that then, as I add another node, the scattering length flips from being negative to positive. Okay, so if I do that, and in fact the scattering length becomes dependent on the position of the last bound state, as I move the position of the last bound state, I modify the scattering length as shown in this diagram. Okay. So how do we move the bound state around, right? Because this looks a little bit like a Feshbach resonance. Okay, I can't go into the lab and stretch the depth of the potential, but I can use the fact that I have alkali atoms, and alkali atoms have different spins. They have hyperfine structure, and so I can have a copy of this potential with a slightly different internal state, separated by the hyperfine splitting. And this higher potential, my atoms are colliding on the black one, but this higher potential can have a bound state, which is now close to threshold. Then I add a magnetic field, and I can shift these two relative to each other because they have different spins. And if I have some spin coupling between these two channels, I mix some of this bound state into this scattering, this open scattering channel. Okay? And so this slide illustrates that. What will happen is I will ramp up the magnetic field. You'll see this bound state move. You'll see this crossing, and you'll see the pole in the scattering length. Okay, so as I ramp up the magnetic field, this crosses, I get this crossing, and I get a pole in the scattering length. So this is the origin of a Feshbach resonance. Okay, and as Mikhail said at the beginning, this is where I started my career in ultracold physics. Back in 2000, we made a rubidium-85 BEC, which has exactly this kind of resonance. And I'm sure you've come across this Gross-Pedievsky equation that describes the BEC, and this interaction term A is controlled by the Feshbach resonance. And it allows us to modify the BEC properties. And then later, we also made bright matter wave solitons where we have a small attractive BEC, attractive scattering length, so that the BEC now doesn't disperse. If I let it go, it no longer spreads out because the attraction is holding it together. So this has become a very important tool in ultracold physics. Today, we're going to use the other aspect of the Feshbach resonance, which is this avoided crossing with a molecular state. Okay, and so for what I'm going to talk about, it's convenient. We always express zero energy as the atomic energy level. So just rotate this diagram. And then the picture is if I start with two atoms and I sweep across this resonance at the right speed, I will go directly into this molecular bound state. And that way I make molecules. So this is a simple measurement. We can illustrate in cesium, just cesium alone now. We can make cold atoms at about 20 Gauss. There's a resonance here, which comes from this bound state crossing the threshold. So if I sweep the magnetic field across this resonance, I should go into this bound state. This bound state has a different magnetic moment from the free atoms. So if I do this in the experiment and turn off the trap and apply a magnetic field gradient, I can separate the atoms and the molecules. Always in these experiments, we break the molecules apart and image them, and image the atoms at the end. We have no direct way of imaging these molecules. Okay, and this is what it looks like. Okay, so we do that experiment, and the magnetic field gradient is set to slightly over levitate the atoms. So the atoms move up, and this cloud that is falling is a cloud of molecules, and it's a cloud of cesium-2 dimers. And from the rate at which they fall and the rate at which they expand, we can get their magnetic moment and their temperature exactly matches that of the atoms. Okay, so we've created ultracold molecules just by sweeping across this resonance. So what does this look like for rubidium cesium? Okay, so our challenge is to go from these free atoms all the way to this ground state. It's a little bit more complicated in rubidium cesium because this is what the bound state picture looks like. Okay, So we have to sweep across this resonance, which goes into this weakly bound state, and then we go all the way down to the next resonance to make a molecule that has a different magnetic moment here. I want to point out the energy, right? So this is bound by about 2 megahertz. The molecule that we want to create is bound by about 4,000 wave numbers. A wave number is 30 gigahertz, okay? So this is a very, very, very weakly bound molecule. It has none of the properties that we want for our experiments, like a dipole moment. We have to transfer it down here. But we can see those molecules, just as we did with cesium. And in our bulk gas experiment, we produce about 5,000 of those molecules. You see them here in exactly the same kind of measurement. We then need to transfer them to the ground state. We do that optically using this Stirrat process. So we need a transition in the excited state that has mixed character, because our Feshbach molecule is predominantly triplet, and we need to go to a predominantly singlet. Well, we need to go to a singlet ground state. So we need a mixed state up here, but they exist. We can find those. And then we need to find the laser that addresses the ground state. And here we want to go to the vibrational ground state. We also want to go to the rotational ground state. And if we look very, very carefully, we also want to go to the hyperfine ground state. Okay, so we really have to do this spectroscopy very carefully to make sure we're addressing exactly the transition we want. And then we simply have a 3-level system, right? We have this hyperfine ground state, we have the Feshbach state, and we have some excited state. And the physics maps onto this simple picture where we have the Feshbach state and the ground state and 2 coupling fields. And the nice thing about this physics is it has a dark state. By a dark state, I mean, if you solve this Hamiltonian, you find there's a solution that only contains states 1 and 3. And that's important because state 2 decays. So you never want to put population into state 2 because it will be lost from the experiment. And this dark state depends on the ratio of these Rabi frequencies. And so in Stirrat, what you do is you apply pulses of light such that the Rabi frequencies on these 2 fields change with time. And it's this so-called counterintuitive pulse sequence where you first apply this field, which prepares this as the dark state. You then ramp off this field as you ramp on this field. And at the end, the dark state becomes state 3. So this coherent evolution swaps the population from the Feshbach state to the ground state of the molecule. And there are some technical details on achieving this. One is on the coherence. You need certain Rabi frequencies to be adiabatic, and you also need good lasers. And cut the long story short, we can make the lasers suitable by locking them both to an optical cavity and getting their laser line widths down below 1 kilohertz. So then Stirrat looks like this. Remind you, we're trying to couple from this state to this state without populating this. We do the Stirrat sequence. We see the Feshbach molecules disappear. We wait a short amount of time. We reverse the Stirrat sequence and break the molecule apart, transferring it back to the Feshbach state, break it apart, and we see this recovery of the signal. Okay, so this is transferring at 92% probability to the ground state and coming back, and it gives us a state-sensitive detection. Okay, it's only addressing this one hyperfine state. And then, of course, we can break this sequence apart and interrogate the molecule with microwave fields and do our experiments. Okay, so this is the basis for what we do. So just to recap on this part on how we make the molecules, start with 3 atoms. We use magneto-association to couple them into a very weakly bound state, a Feshbach molecule. Then we use laser fields to transfer them again coherently to the ground state. And at that point, we can interrogate the molecule, we can trap it, we can poke it, we can tickle it with microwaves, do our experiment. We then do the return Stirrat, which only addresses this lowest hyperfine state, and we can make observations of what we've done to the molecule. Okay. So I was going to take questions here, but I won't. I'll carry on and we'll take questions at the midpoint. But please bear in mind if you have any questions on how we make molecules. So I want to move on to talking about, okay, well, now we've got our molecules, how do we control their internal state? And so we're going to talk about microwave spectroscopy, doing Ramsey measurements, critically coherence, and as this should be magic trapping, not magnetic trapping. Okay, so spectroscopy, first of all in free space. Okay, let's not worry about trapping the molecules. So I've shown you this diagram before. Let me explain a little bit what it is. We've prepared our molecule in this rotational ground state, in this red lowest hyperfine state. These are all the hyperfine states that are accessible. And in n equals 1, we now have 96 hyperfine states. These are all grayed out mostly. The ones which are allowed by electric dipole selection rules are shown here in color. So we drive this microwave transition at 980 megahertz and we can access these states. Okay, and although these states are very close together in frequency, when we do a microwave transition, all of the line widths are Fourier limited. Okay, so if we use, for example, a 1 millisecond microwave pulse, then we will get a 1 kilohertz line width. Okay, so we can easily resolve all of these transitions, we can map them out, and in so doing, we actually learn the hyperfine parameters, if you like, of the molecule, the properties of the molecule. And it's these numbers that actually allow us then to construct these diagrams and understand the structure of the molecule. So this was a very important first step in our journey. I mean, this dates from 2016, but really it allows us to then understand the structure of the molecule fully. And then the question is, so this is all in free space, no trap. What happens in a trap? Okay, so this took a few more years. This is now 2017. This is what we see in a trap. Okay, so this is essentially the same diagram. So we're looking at the transition frequency plus 980 megahertz up to the first rotationally excited state. But now we're doing it as a function of the trap intensity. And each one of these points is a spectrum measured like this. And we can map out all of these transitions. And what you see is we've got this wonderful spaghetti. Okay, the different colors are for different microwave field orientations or different transitions in the molecule, if you like. But the spectrum looks a mess as a function of intensity. I should say the lines are theory, so we understand the mess, but it's not ideal for many of the experiments we'd like to do. So why is it so complicated? Okay, and this is where the complications of the molecule kind of come to the fore. So the thing you need to understand is that the polarizability of a molecule, that's how it responds to the light, is different if the light is polarized orthogonal to the bond axis or if it's polarized parallel to the bond axis. Okay, and so another way of putting that is there's an isotropic component, which is basically the average of these polarizabilities, and there's an anisotropic polarizability that comes from the difference between these. The isotropic polarizability is the same for all rotational states, so that's good, and it provides trapping. The anisotropic polarizability is actually negligible in the ground state of the molecule, the rotational ground state, but as soon as you go up to a different rotational state, it mixes Mn, the projection of the rotational angular momentum, and therefore mixes Mf. So this mixing of states that you see here comes from this interaction. And we can write out a matrix that describes this interaction. I don't want to go into the details, but the important point is there are both diagonal terms that shift the energies of the states, but also these off-diagonal mixing terms and they have this dependence on the polarization angle, beta, okay? And they're all proportional to this anisotropic polarizability. So because it depends on the angle, I should have emphasized this was for the laser polarized perpendicular to the quantization axis. I get a different picture if I put it parallel. It looks a little bit simpler, but still there are shifts. And actually, for every angle in between, I get a different picture. Okay, so this is very complicated. But the important thing is, wherever you look in this diagram, generally there's an intensity dependence to the transition frequency. So for example, if I look at this state, which is very simple, depending on the intensity, I have a different transition frequency. And this is a problem, right? It's a problem because I have molecules in a trap moving, they sample different intensities. And as they sample different intensities, they have different transition frequencies. And this leads to dephasing of the rotational coherence. And it also completely suppresses the spin exchange interaction that I mentioned at the beginning that we want to use to do interesting physics. Okay? So how do we probe these dephasing effects? We use Ramsey interferometry or Ramsey spectroscopy, which I'm sure you've come across, but the basic picture is we use a pi/2 pulse, a microwave pi/2 pulse, to prepare an equal superposition of two states in the molecule. We then wait. This superposition has a certain energy associated with it, so it evolves. We do another pi/2 pulse, which effectively forms an interferometer. And we compare how the molecule has evolved to how the microwave field has evolved in that time. Okay, and so in changing, for example, the time or the detuning of the microwave fields, we get fringes. And these are the famous Ramsey fringes that allow you to do more precise measurement. Okay, and this is what we see in free space. We can vary this evolution time, and in free space, we see this kind of behavior. So here, the contrast, which is the peak to the minimum, is always high. Okay, this signal always goes to 0. So we have full contrast fringes. The loss in signal is because the molecules are actually falling out of our Dirac beams. Okay, so in free space, we have good contrast, no decoherence, we just have loss. So what does it look like if we do this in a trap? I've told you that in the trap, it should be bad, and it is bad. Okay, so here, this is 2 milliseconds. If I do it for this state B, where this linear shift, then this dephases very rapidly, this Ramsey measurement. So I have maybe 0.1 milliseconds. If I'm smart, I could use this state where the intensity dependence is much flatter, and I get longer coherence, but it's still only about 1 millisecond. Okay, and this is a problem, and it's a problem for all molecules. I won't go into the details. This is not specific to rubidium cesium, but this is a selection of experiments from around the world where people have tried different tricks to kind of get around this problem. And you see, coherence times of 50 milliseconds, 100 milliseconds, 60 milliseconds, okay, by throwing all the tricks at it. So we have I should emphasize that the tricks that are essentially played here are manipulating that matrix I showed you. So we've developed a different approach, which is actually to manipulate alpha 2, which is the anisotropic polarizability, the prefactor in front of that matrix. And the idea is quite simple. If we made alpha 2 0, then the problem would go away. So how do we make alpha 2 0? We recognize the fact that the two polarizabilities come from completely different transitions in the molecule. Okay? So if we tune the laser close to a transition of a particular type, then we should be able to modify one of the polarizabilities without affecting the other. And we use this 1145 transition, which is the X to B transition in the molecule, and that allows us to tune alpha parallel, but it's far detuned from any transitions that affect alpha perp. Okay? So alpha perp effectively remains unaffected, and we tune alpha parallel, and then we can find a wavelength where alpha parallel is equal to alpha background value of alpha perp, which makes alpha 2 0. And then the whole problem should go away. That's the theory, okay? So let me just reiterate that. So as we change the wavelength or the detuning of this laser, we've got these vibrational levels in the excited state. Associated with each of those, there's a transition that gives a pole in the polarizability for alpha parallel. Okay, these are the two poles, but does not affect alpha perp. And you can see at this point, alpha parallel and alpha perp are the same. And expressing this in terms of the polarizability of the rotational ground state and the first rotation excited state looks like this. And again, at this point, those two polarizabilities are the same. And this creates this magic condition, okay, where the two potentials, the potential for a molecule in the rotational ground state and the rotationally excited state, look exactly the same. And at this point, wherever the molecule sits in this intensity Gaussian beam, it has the same transition frequency. So there's no dephasing. Whereas away from this, these potentials look different, and we get this dephasing problem. I should point out that this detuning is actually very large compared to the line width. So we're 186 gigahertz away from a line which is just 14 kilohertz. Okay, so that's far detuned, so we don't need to worry about laser scattering or loss of the molecules. Okay. So we can do this in our experiment. We can shine on light at this wavelength, and we can measure the microwave transition and see how that transition shifts as a function of the laser detuning. And we see those poles, exactly as I showed you in the theory. We see the poles exactly where the vibrational levels of the excited state are. And above each one of these is this magic wavelength where the shift compared to free space is 0. Okay, so we have many magic wavelengths. Turns out this one is the best because it's furthest from the transition. So now we can return to our Ramsey spectroscopy to try and probe this coherence. And this time we do a slightly different measurement. We still do a pi/2 pulse on the molecule that prepares the superposition on the equator of the Bloch sphere. This rotates around, and then rather than varying the time, we actually vary the phase of the final pi/2 pulse to do the interferometry readout. And this way we get fringes, and the contrast of those fringes is the indicator of how close to magic we are. So in this kind of raw data, we see as we tune the laser, the trapping laser across this range, we see this fringe contrast change quite dramatically. And this allows us to identify magic. We can do this for many transitions in the molecule. Okay, so this is data for this 0 to 2 transition, which we drive with 2 microwave photons. We can change the Ramsey time and weight holder, and then this gets sharper. So we can really pinpoint where magic is. And we can do it for different combinations. So 0, 1 superpositions or 1, 2 superpositions. They're all in roughly the same region. They're not exactly the same detuning, but we understand that. And so let me focus initially on this 0 to 2 transition, which we have to drive with 2 photons, 2 microwave photons. And the reason we want to use this is there's no direct transition dipole between them, and so there should be no dipolar interactions in the experiment. And then we can plot the fringe contrast for this superposition as a function of the Ramsey time. And this is the raw data we get. And already we get a time which is almost a second. And in the measurement, this was limited by how well we could lock the laser, the magic laser that we're using to do the trapping. And if we just put in a pi pulse to do a spin echo, then we can see no decoherence at all of this superposition. Okay, so this is 1,000 times better than anything we've ever produced in our lab, and it's way better than any other experiment in the world. Okay, and it really gets rid of this dephasing problem that plagues the field. Interestingly, this time is now long enough to see dipolar interactions. Okay? So how do I make dipolar interactions? Well, I use a different superposition. So if I use a superposition in the molecule, say 0 and 1, then that actually the molecule then becomes an oscillating dipole. Okay, this superposition has the property of an oscillating dipole, in this case a rotating dipole, and now my gas of molecules is actually an interacting gas of rotating dipoles. And those interact and they dephase because of the random positions and motion of the molecules. So I actually see a shorter coherence time, but that's good because it's due to dipolar interactions. And this fits remarkably well with a theoretical treatment of oscillating dipoles interacting. Crucially, the reason we investigate different state compositions is they change the dipolar strength. Okay, and so I can then look at this coherence time as a function of the dipole moment and see that for large dipoles I have small coherence time, small dipoles I have long coherence time, and if I replot that in the right way as 1 over the dipole squared, I get a linear behavior, which is conclusive evidence that now we have dipolar interactions in our gas, which is great. Okay, and this all comes from the magic trapping. The next step, so this is a random gas of thermal molecules. Okay, the next step would be to fix the molecules in space, and then we can control this interaction because this interaction depends on the distance, 1 over the distance cubed. So if we fix the distance, we get a fixed interaction. Good. Well, let me continue. So a brief recap. I've told you how we make a molecule, and I've told you how we control its internal state with microwaves and how we can engineer very long coherence. Okay, so we can prepare superpositions of rotational states that maintain their coherence for seconds. The ingredient we don't have is any kind of spatial control. Everything I've told you so far is just in a gas of molecules, which is very uncontrolled. So the next part is going to be controlling the motion. I'm going to tell you how we can then assemble molecules in optical tweezers and then engineer entanglement, and how we can then progress that to optical lattices. So I'm sure you've probably come across already in this series the idea of an optical tweezer. In the atomic physics world, what this relates to is a very tightly focused laser beam from a microscope objective into our ultracold gas. And when we do that, the typical traps are about a micron in size, and there's a phenomenon called collisional blockade, which means that only one atom can be loaded into that trap. It's loaded in such a way that roughly it's 50% probability. But the beauty is, if we then shine on the laser cooling light for that atom in that trap, we can collect the fluorescence and look at it on a camera, and we can see that there's an atom. So this was first done many years ago, and you see the evidence of single atoms entering the trap and leaving, and you see that on the image. So this red dot indicates there's actually an atom in a trap there. Nowadays, people can do this in 2 dimensions, even 3 dimensions, okay? And so this is a randomly loaded array of atoms. But because we can detect where the atoms are, we can rearrange them. And the device is called acousto-optic deflectors that can move the traps around. And essentially, we can take this random loading and make a perfectly ordered array. And the most beautiful example of this is from the Lukin group in Harvard, that actually not only do they make their ordered array, they move their atoms around in such a way. So if I play this movie again, what the red circles indicate is they're doing actually a quantum gate each time with Rydberg atoms. Okay, so this is the basis for doing quantum computing with ultracold atoms. Okay, all enabled by this optical tweezer technology. So how do we use this to make molecules? It's actually quite simple. So again, we have a big lens. We focus light down to make tweezers. The difference is we use different wavelengths, and the different wavelengths allow us to trap different atoms. So for example, this 817 wavelength will only trap rubidium, and this 1065 wavelength will predominantly trap cesium. Okay? And this way we can individually trap and address our atoms. And so this is signatures from our experiment where you see a single cesium atom and we can detect it because of the photon counts compared to if the atom wasn't there. Okay? And it's normal in these types of experiments to make your local landmark. We do this with a device called an SLM, which allows an arbitrary array of traps. And this is called the Angel of the North, a sculpture near Durham. And this is our rendition of it in single cesium atoms. Okay, 50 microns across instead of 50 meters across. So how do we make molecules in this setting? So this is the recipe. We first we load arrays of atoms. We rearrange them and we do really advanced cooling on them, which I don't have time to go into the details, but it's very important. We then merge these arrays to have atom pairs, and then we just do what I've already told you. We do magnetoassociation and stirrup. It doesn't work on every site, and so on some sites we form a molecule, on other sites we still have atom pairs. But we can turn the rubidium tweezers back on and pull out rubidium atoms. And where there's a molecule, this has no effect, but where there's an atom pair, we get an atom in this now green tweezer array. So this flags, it's like an error flag. It tells us where the molecule formation didn't work. We then do our experiment and we break the molecule apart at the end, like I've always done, and separate the atoms into separate tweezers. So then the final image, we look at 3 arrays. This indicates there was a molecule present. This indicates that it didn't work there, and so on. And so by post-selecting on these final images, we can look at the sites that only have a molecule and do some measurement. This works remarkably well. So magnetoassociation, where this is now going across that avoided crossing, changing the speed of the magnetic field ramp, it saturates to about 50%. And this is a technical point. This really relates to how well we've cooled the molecules. So in the tweezer, to form a molecule using magnetoassociation, the atom pair has to be in the ground state of the tweezer. So the tweezer is a harmonic trap with energy levels. We have to cool it all the way to the ground state of the tweezer. And we don't do that perfectly. And on average, the atom pair occupation is around 56%, which is what limits this. Stirrup is very efficient. It's 96%. And so overall, we can create a molecule, a ground state molecule, in about 50% of cases where we have an atom pair. And crucially, this molecule is actually in the ground motional state of the tweezer because it's inherited the motional state of the atoms. So this is now full quantum control of the molecule, right? It's prepared in a single internal quantum state, but it's also in a single motional state of the trap. Okay, and so this is a really important advance. Rather than having molecules sloshing around in the trap, I have a molecule with a well-defined wave function at the bottom of the trap. The tweezers allow us to do lots of interesting things, okay? So critically, again, we can drive microwave transitions, but now we can do a multi-state readout, okay? So this is the protocol illustrated here. So we might have a site which has a molecule in n equals 0 and one with n equals 1. We can break the n equals 0 molecule apart with stirrup. Remember, it only addresses the ground state. And we can separate those atoms, leaving the cesium atom where it was and moving the rubidium atom to this site. The n equals 1 molecule is completely unaffected by this. So then we can do a microwave pulse, transfer it to n equals 0, break it apart, but this time move the atom, the rubidium atom, into a different array, right? And then we just make a measurement. So if the rubidium atom is here, the molecule was in n equals 0. If the rubidium atom was here, it was in n equals 1. And so this is a Rabi oscillation driving the microwave transition in the molecule, doing this multi-state readout, post-selecting on where the rubidium atom is. So I can tell if the rubidium atom is here, I was in n equals 0. If the rubidium atom is here in this other trap, then the molecule was in n equals 1. And this is really important because it mitigates a lot of errors that could occur. If you think about it, if I wasn't detecting n equals 1, then when I drive the microwave transition, that looks exactly like I've lost the molecule, right? Because I've just got no signal. So this is a really important tool that comes from using optical tweezers. So then the exciting question is, how does the magic trapping that we developed in the bulk gas work in the tweezer? Okay, so this was a bit of an afterthought for our experiment. And so we had to couple this light in through the imaging path. It's not ideal. The waste is pretty big. I said tweezer wastes are normally about 1 micron. This is closer to 2 microns because the lens was not really designed for this wavelength. But we've upgraded how well we lock the laser. Remember, that was a problem earlier. And so we should be able to do some nice measurements. Okay, so what does this plot show? This looks a bit complicated. So again, we're doing Ramsey measurements, and we're looking at Ramsey fringes after about 80 milliseconds, okay? And we're varying the detuning of the laser that we're using to form the magic wavelength, okay? It happens to be from the cavity mode that we're locking to, but think of this as detuning from the transition. And these measurements allow us to measure the light shift due to the laser in the tweezer. Okay, and this is very precise. So this is shown here. This is the transition frequency minus the 980 megahertz, but this is now in hertz. So we're really measuring hertz level shifts in the molecular transition. And these are all, the curves are all for different intensities. And what you notice that at this point, they all intersect. And that's the magic wavelength, right? Where there's no shift. And I can plot this differently. I can plot it as a function of intensity. And you see for this particular detuning, then the line is horizontal. There's no intensity dependence. And that's the magic condition, okay? And all of this data can be fit with one number, and that's the sensitivity of the transition to the laser detuning and laser intensity. And it's this number, about 100 millihertz, which for typical parameters will give us a coherence time in the tweezer of 66 seconds. Okay, so this is really minute scale coherence now for these transitions in the tweezer. And we can do a Ramsey measurement where we vary the time. Actually, this is in 2 different tweezers. One is shown in red and one is shown in blue. Neither of them are exactly magic. They're slightly detuned. But the measurements now go out to 2 seconds. And you see we've still got beautiful Ramsey fringes at 2 seconds, which means we can engineer this coherence to be very, very long. And I should emphasize, there's no tricks here. There's no spin echo. There's no sophisticated dynamic decoupling pulses. This is just using the correct wavelength, the magic wavelength. Okay, so in the tweezer, this is absolutely great. So now we can actually use this to exploit the interactions. We saw the dipolar interactions in the bulk gas. We saw that they led to dephasing. Here, if we put the molecules at a certain separation, then that interaction will be a certain energy. And rather than dephasing, it should actually have a one energy, one time scale associated with it. And we can actually use this to do entanglement of the pair of molecules. There's a problem or a challenge. Our tweezers are quite big, okay, which means we can only get them about 3 microns apart. So the typical interaction we'd expect is only about 6 Hertz. Okay, if you've come across anything about doing entangling operations in Rydberg atoms or things like that, where this interaction energy is usually megahertz, then you'll understand that this is incredibly weak and is not the kind of basis that you want to use for building a quantum computer. But it really illustrates how powerful the magic trapping is. Okay, so we do need to make both the tweezers magic, and I can explain how we do that if you ask. But the upshot is, if we take a molecule and put it in either tweezer 1 or tweezer 2, just one molecule, we can measure these transitions and we find them in exactly the same place. This scale is Hertz, so the difference here is a 0.2 Hertz or so. Okay. Then we can put 2 molecules into the traps, so then side by side. Now, if we do the spectroscopy, we should actually see these interacting states, which are shifted by this spin exchange interaction. Okay, and they are. So I do the spectroscopy now, I see a shift. So this is where I'm driving the transition in the molecule. And that shift is 2.6 Hertz, which is exactly what I expect, about half of the predicted interaction energy. Okay. So this is seeing the interaction, the dipolar interaction at a fixed energy due to these 2 molecules. And now I can sit here and drive the microwave transition, and then you get a collective enhancement of the Rabi frequency. So it should go √2 times faster because there are 2 molecules involved in this superposition, and that's exactly what we see. So now we can entangle the pair of molecules, and we do that again using a Ramsey sequence. So if you do a Ramsey sequence, 2 pi by 2 pulses, and let the system evolve, then what you should read out is actually given by this wave function. Okay, you should see oscillations between both molecules being down and both molecules being up, and the oscillation is controlled by the interaction strength and the time. And that's exactly what we see in the experiment. Okay, we see oscillations between up, up, and down, down. And if we stop or set the time to be here, then we should prepare an entangled state, one of the Bell states. Okay, it's a superposition of down, down, and up, up. And to probe this Bell state, the normal thing to do is add another pulse where you vary its phase, and then you measure something called a parity oscillation. And it looks like this. And this is really just telling you whether this is a coherent superposition of these 2 states. And we get a very nice oscillation with high coherence, high contrast. We combine this with the populations that we measure here, which is basically 50% up, up, 50% down, down, and nothing in the up, down states. And this gives us a fidelity for the entanglement, okay? And so here we've entangled a pair of molecules with really high fidelity, pushing 0.98. 1 is the limit, of course, but this is using an interaction strength of just a few Hertz, which is really quite remarkable. And this is competitive. In fact, it's probably better than the other experiments that have used this with molecules. There were 2 experiments in 2023 with calcium fluoride, the laser-cooled molecules, and around the same time as ours, an experiment using sodium cesium, and their fidelities are all a little bit lower than ours. Okay. One thing you will note, though, that their interaction energies, here it goes up to 700 Hertz, are all a lot higher than our 5 Hertz. So we'd really like to get our molecules closer together to push this technology. Now, how do you get molecules closer together? Well, one solution is to use lattices. So we have another apparatus, which is a quantum gas microscope, where we have an optical lattice, which would put the molecules around 800 nanometers apart, and then we'd have interactions which are 280 hertz rather than 5 hertz. Okay? And this experiment is now becoming operational. So it's very complicated. One of the complications is we do optical transport from this 3D Mott region of the atoms into the glass cell to give lots of access for this objective. This took a long time to set up, but it now works. One of the details I haven't talked about is rubidium and cesium really don't like each other. So we actually do transport of one species first. We then move that species out of the way so that we can transport the second species in. And then we trap those two species separately and cool them separately before finally merging them. Okay. But as I said, this is all working nicely. We can make double BECs in this system, now separated by a half a millimeter or so in these separate traps. And that's the perfect situation for controllably loading the atoms into this lattice. We can also just shove the atoms together in this final stage and make some molecules, and we've done that. We have beautiful imaging in this setup. So these are very sparsely loaded lattices just to be able to individually see the atoms. So each of these blobs is an atom. And the empty ones are used to get the background, and we get the same kind of count histograms that we see in the tweezers. And we can also do this with a lot of atoms. And then you can see this filling of the lattice, and we can really identify individual lattice sites. This is all with atoms. Okay? But excitingly, we can now do this with molecules, right? So this is now a cloud of molecules, or rather it's a cloud of atoms that were molecules. And we can actually drive the microwave transition in the molecule and do the same kind of mapping that we did in the tweezers, but now rather than to space, we map to species. So if the molecule was n equals 0, we detect a rubidium atom. And if the molecule was in n equals 1, we detect a cesium atom. So again, this is this kind of Rabi oscillation of the microwave transition mapping to different species. And data from just a week ago, we can now also put an addressing beam into this system. So these are molecules in a lattice with an addressing beam, which allows us to flip the spins in a local region, which is a wonderful starting point for then allowing these spins. If the molecules are pinned, these spins can migrate through the spin exchange interaction. So this platform is looking very, very exciting. And there's a lot to do, but I think the many body physics proposals I talked about at the very beginning are within reach of this experiment now. Okay, I'll skip the questions. We'll save those for later. And I want to move on to the final part because I promised Mikhail we'll get to BEC. And the last element we need to control in molecules is collisions. Okay, so I've told you how we can control internal state, motion, coherence, but we also need to control collisions. Okay. And so I'm going to tell you about loss of molecules, shielding, and then actually molecular BEC, which I think will bring us to a nice end given the topic of these lectures. And I'm imagining that you've already understood that collisions in the ultracold world are phenomenally important. Okay, in atomic physics, we use them for cooling the atoms. We use them via Feshbach resonance to control the BEC properties, to control many of the properties in lattices are set by the collisions, this contact interaction. So it's just as critical that we can control them in molecules. So the story, right? The first experiments using heteronuclear molecules were in 2008 with KRB in the Giller group, Junyi and Debbie Jin. And a couple of years later, they had this nice paper in Science, which basically reported our molecules go away, right? So this is molecular density as a function of time, and you see this quite strong and rapid loss. These are KRB molecules, okay? And everybody realized quite soon what the problem was. So this plot, so KRB molecules, they're using a fermionic, so they can only collide with p-wave collisions. So this is the loss rate as a function of the temperature, and this temperature dependence is indicative of this p-wave barrier, the centrifugal barrier that you have for p-wave collisions. If they put the molecules into a mixture of states, then you get S-wave collisions, and there's no temperature dependence, and the rate is a lot higher. Right? This is nearly 200. This is 10. Okay, so something is happening here, which is very fast and very destructive. Okay, and what that something is chemistry. So I realized with these pioneering experiments that this bialkali molecule, KRB, colliding with KRB can go to K2 and RB2. Okay, this is an allowed chemical reaction. And you can see that it's allowed just by looking at the energetics, so the binding energy, if you like, of the individual molecules. And the difference for the KRB case is about 9 wave numbers lower in energy, right? Which basically means this configuration is lower in energy than this configuration. So when these molecules collide, they're free to undergo this reaction without a barrier. Luckily, there's a lot of molecules, including rubidium cesium, where that's not the case, right? For rubidium cesium, rather than being -9 wave numbers, this is +29, which means you need a huge amount of energy in order to make this reaction in rubidium cesium. So rubidium cesium molecules should be stable, and we should be able to do experiments for long times. Okay, so then we make the measurement. This is the number of molecules as a function of time in our trap, and it looks pretty similar, right? The molecules go away quite quickly. And you can look in this table and say, okay, what about sodium, potassium, sodium, rubidium? Sodium, potassium decays. Sodium, rubidium decays. So all the molecules are showing this loss, right? Whether they have reactive collisions or not. So what's going on? And this really was a puzzle for many years. And then John Bone put forward this idea of what he called sticky collisions in this paper. So let me explain what this relates to. So what he argued is that molecular scattering is highly resonant. I should point out, it is very, very hard, if not impossible, to do really accurate collision calculations for two molecules. Okay, and that's because if I think about two molecules, rubidium and cesium, then they actually collide on an anisotropic four-body potential energy surface. What does that mean? That means if I have two rubidium cesium molecules, if they collide rubidium to rubidium, that will be different from if they collide cesium to cesium, or if they collide side on rubidium cesium to rubidium cesium, right? So this problem is computationally very hard, if not impossible. So people have to use different methods. And what John argued was he looked at this problem and said, well, there are very many bound states close to this collision threshold in molecules. We know from what I told you about atomic systems that if you have a bound state close to threshold, you can get a resonance. So that means there must be many, many, many resonances in molecules because of this high density of bound states. And he did kind of statistical type calculations because he can't do these potentials exactly, but he made some arguments that yes, there should be lots and lots of resonances, which means the molecule is somehow sampling lots of resonances in a collision. And he argued that this leads to what's called a sticky collision, where the molecules come together, they form this complex, this resonant complex, um, and that lives for a certain amount of time that depends on the density of states here. Okay, this might be a bit abstract, but John also is a great communicator, and at a meeting in Santa Barbara, he had this beautiful analogy. And so what it's like is our molecule is an insect, a wasp, and it flies into a bottle. This is the collision complex, right? And it gets stuck there because of all these resonant states, but eventually it comes out, okay? Because energetics means it has to come out as a free molecule. So that's the sticky collision picture, right? It takes a certain amount of time before these two molecules can separate or the insect can get out of the bottle again, right? The problem is if while the insect is in the bottle or the molecules are in this collision complex, something bad happens, then we lose the molecule and the insect gets squashed, right? So that's this sticky collision picture. And actually, in John's paper, he argued that if the lifetime was long enough, this collision complex could just collide with another molecule, and that would give a three-body loss. Okay. Later, 6 years later, Thijs Kalman and his collaborators did a more sophisticated calculation, and they showed that the lifetime of the complex for rubidium cesium should be only 0.25 milliseconds. And at this point, that's not long enough to have this three-body collision problem. But they also showed if this complex forms in the presence of laser light, then the laser can excite the complex, and that will lead to very rapid loss. Okay, and so this should lead to a two-body loss decay limited by the formation of these complexes. And we fit our data and we see very nicely that it's two-body. It's not one body, it's not three-body, it's this two-body, which seems to indicate this sticky collision picture. So the picture is we have two colliding molecules. There are all these resonant bound states when we form this four-body complex. If nothing else happens, it should go back to free molecules because it can't access these reactive channels because they're higher in energy. But if we do this with a laser present, the laser will excite the complex. Once it's up here, it decays somewhere, not back to the ground state, and it's lost. Okay? And we were actually able to prove this by using a modulated trap. So we switched the trap on and off very rapidly such that the molecule spent an appreciable fraction in the dark. And then we could compare that to the case where light was always present. And by varying this modulation frequency, we could vary the time the molecule spent in the dark. And we saw that actually the loss was less when the molecule was in the dark, which supports this picture. And in fact, if you analyze this data, you can get a complex lifetime out of this measurement, which is about half a millisecond, which looked pretty good compared to the 0.25 milliseconds. And so we thought at this stage, we understand molecules. We know what the problem is, okay? It's another story, but it's not quite. I would argue that we don't quite understand. So this nice paper from 2023 summarized many experiments, and they highlight that not all experiments fit so nicely to our measurement. But they say the behavior of complexes is not fully understood. In some cases, their lifetime has been measured to be many orders of magnitude longer than the models predict. And so I think this is still an open question of this behavior of how molecules collide. But this loss, is a problem, right? Because if we want to make the molecules colder, we don't want them all to go away. We want to be able to do evaporative cooling in a controlled way. Thankfully, there are solutions, and those solutions involve shielding. Effectively, they're using the dipolar interaction to stop the molecules reaching short range. So one solution is to apply an electric field. And then if you have two molecules both in the first rotationally excited state, then at some field they become resonant with a pair of molecules in 0, n equals 0, and n equals 2. Okay? And at this resonance you have dipolar coupling, and that leads to a barrier, okay, in the collision potential. So by sitting at this orange line, then as two molecules approach one another, they should experience this barrier and should not be able to access the short range where the chemistry happens. And that works. In this paper from Junyi's group, they showed that by tuning the electric field, you can see these resonances where the loss rate just above the resonance is strongly suppressed, and just below the resonance, it's enhanced because you actually remove the P-wave barrier. And they showed that you could suppress and enhance the loss in this way. In fact, they used it also to cool the gas to degeneracy, fermionic degeneracy. Similarly, another technique that's developed by the Munich group was to use microwave fields instead of DC electric fields. This requires circularly polarized microwaves, but the essence is the same. I mean, the physics is slightly different, but now what you're doing is dressing the molecules such again you get this repulsive barrier due to the dipolar interaction. So when two molecules approach one another, they repel because of this dipolar interaction. And they showed that by controlling these microwave parameters, you can suppress the loss. So by going to this detuning, you suppress the loss. At the same time, you massively enhance the elastic collision cross-section, because that's set by the dipole that's being introduced in the system. So now we have a huge ratio of so-called good to bad collisions. So for evaporative cooling, we need elastic collisions and not many lossy collisions. That's what you have here. And so they were able to show that you can cool this Fermi gas to quantum degeneracy using this microwave shielding. And then finally, bring us to the end and full circle on the topic. In 2024, there was this wonderful paper, which is a Bose-Einstein condensation of dipolar molecules, okay, using sodium cesium from Sebastian Will's group. And again, they used the microwave shielding. Okay. A slight subtlety is that they use this strong circularly polarized microwave field, but they also add an additional field, which is pi polarized. And what they discovered in their work, if you just have this circularly polarized field, then the actual potential, which was present here as well, has an attractive well. Okay, so as a function of distance, there's an attractive well before you get to this big barrier that stops the chemistry. But the attractive well can have a bound state. And if it has a bound state, then you can get high three-body loss. Okay, so this additional microwave field eliminates the attractive well, and they can get the purely repulsive barrier. And when they did that, they get good evaporative cooling, and you see the classic signature of cooling to BEC and the emergence of this anisotropic distribution due to the trapping potential. Okay. So I think that pretty much brings me to the end, and we're almost out of time. So what's the conclusion? I think we have all the tools available for this field to use ultracold molecules to do exciting experiments with dipolar BECs, to put them into lattices, to do entangling operations, to do many-body physics. It's a really, really exciting time. So the conclusion has to be that two atoms are better than one, right? And with that, we can do all these wonderful experiments, okay? So I just want to end by acknowledging, I've spoken about a lot of results today from my group, and this comes from this amazing team of people who actually do the experiments. Many theory collaborators, and I'm grateful for funding from many agencies. So thank you.
Thank you very much, Simon. Thank you for your amazing, extremely well thought out and clear lecture. And now it's time to go to the Q&A session. I see that we have some questions already here. But we, of course, encourage more participants to input their questions in the Q&A section in Zoom. So, Simon, the first question is there a set of favorable properties which give rise to magic optical wavelengths in a given diatomic molecule?
Yes. So what's really important? So why does it work so well in rubidium cesium, you might ask? And the reason is it works well is because it's actually at 186 gigahertz, which means it's far away from the transition. And why is it far away from the transition? Well, that's due to the molecular properties. It's due to the rotational constant in rubidium cesium being very small because it's a big, heavy molecule. And because it's also a big, heavy molecule, the line width of the transition is actually reasonably big. Okay, so in our paper with Svetlana, we set out the conditions for this, and it really depends on those kind of parameters of the molecule. So the magic wavelengths do exist in other molecules. I know in KRB, they've looked at it, and the magic wavelength is about 30 gigahertz detuned from the transition. So I think it's going to be a general tool. It's really just a case of finding the right transition in the molecule to do this. And for anybody who knows anything about molecules, there are many, many transitions. So I'm sure there are options there for other molecules. But I would say we've been quite lucky with rubidium cesium, that amongst the bialkalis, it's perhaps the most favorable for this magic wavelength.
Okay, thank you. Next question. Is it possible to load the molecules directly from tweezer to the lattice and change the lattice spacing after the loading?
Yes. So one of the things, I imagine this has been evident through this series of lectures that everything is possible in the ultra-cold world. It's just how technically difficult is it. So in principle, we could do that. Actually, what we're going to do, give a slightly different answer, is go back to the BEC physics. So we can produce double BECs of rubidium and cesium. And in Innsbruck, they showed a few years ago that you can load the cesium BEC into the lattice, prepare this Mott insulator state where you have one atom of cesium per lattice side. But because of the different atomic properties, the rubidium is still superfluid. And so you can then bring the rubidium into the lattice and let it mix with the cesium. And if you pin the cesium to begin with, you can control the interspecies interaction and make that mixing work very well. And then when you do that, you can actually produce a lot of molecules in the lattice. And so I think that's the way we will pursue. The tweezers, I think what we will do is build small quantum systems. It's quite hard to scale up the tweezers for technical reasons to get to thousands of molecules, but we can build nice, we can build a triangle of molecules, for example. And a triangle has frustration, and so we can explore simple quantum problems with molecules in the tweezer setting. Yeah.
Okay. Another question. Could you please stress again the main advantages of using suitable molecules rather than dipolar atoms?
So the main advantage is the strength of the dipole and the tunability of the dipole. Okay, so the dipolar interactions in molecules can be 1,000 times greater than in magnetic atoms, even dysprosium or erbium, where the magnetic moment is big. So that's the big advantage, plus the controllability of the dipole. Okay, so I can say it's 1,000 times bigger, but I can control it, right? So it could be 0 or anything between. So I have the tunability in the system to control dipolar interactions. On top of that, you throw in the many internal states, And then you've got new possibilities, right? I mean, as a field, we're only just starting to think about, realize the possibilities of using two states in the molecule. And once you put in 10 states, it's a different system entirely. So I think there are lots of exciting possibilities there. Maybe 5 years ago, I would have said, but of course, the ultracold magnetic atoms can make BECs, right? Which means that they've really got control of the motional states of their atoms. And although their interactions are small, their temperatures are really low because they can make BECs. And we can't use that argument against molecules anymore because we can make molecular BECs. So I think we've reached the point where everything you can do in atoms, you can now do in molecules, but molecules are just richer. So really, two atoms are better than one, right? End
We're
of.
coming to it, and I love it. It's great. It's a great slogan. Okay, and going to the next question. Could you please share what phenomena are you planning to investigate with the spin exchange of partially pinned cloud of atoms you showed earlier?
Yeah, so I guess what's next on the agenda for us? Many different directions. So in terms of the tweezers and the spin exchange dynamics and doing entanglement, we want to scale that up. So for example, we could do 3 molecules. A topic I haven't talked about, but one that we work on is to put a Rydberg atom next to a molecule and leverage the Rydberg atom dipole. And I know Mikhail has proposals on this topic. We actually work on it experimentally. I think there's interesting ideas there to use the Rydberg atom to entangle molecules to do spin models. In the lattices and the bulk gases, we want to engineer synthetic dimensions. So we've started to move already to use 3 states in the molecule. We can make 3 states highly coherent, which is like a spin 1 problem. And then you could do entangling operations of qubits. Okay, so that's most of the field of quantum information thinks about qubits, where you just have 2 levels, but we could also do qubits. And that's important because qubits have a higher density of information, which means the scalability problem becomes less of an issue because you don't need so many particles. In the lattice, we want to do itinerant physics of mobile dipoles, or pin it and look at spin transport problems. So the reason we created a region of one type of molecule, one spin state compared to the bulk, is that those spins should then hop in the lattice through the spin exchange. But it's quantum mechanical, right? So every hopping molecule explores every path available to it at the same time. And this just leads to entanglement and strongly correlated many-body states that we want to explore and try and understand, fundamentally how entanglement emerges in these kind of systems. So many, many things, probably too many.
Well, as usually in science, you have many ideas and then 1 or 2 works, right?
Yeah.
These are amazing plans. Thanks for sharing them. Okay, I see another question, perhaps on the easier side. What influences the choosing of the atomic species from the molecule to form the molecules? Are homonuclear molecules just too simple?
Homonuclear molecules are they just as simple? They're actually probably a little bit more complicated in some ways. Certainly making the ground state molecule. The important thing, though, to understand is if you want to access this dipolar physics, it has to be a heteronuclear molecule. Okay? The homonuclear molecules do not have a dipole. And that's very simply, if you take rubidium and cesium, somehow the electron affinity of those 2 atoms is slightly different. So that gives the molecule a dipole. Whereas if the 2 atoms are the same in a homonuclear molecule, that doesn't happen. So there's no dipolar physics. So actually not many people are working on homonuclear molecules anymore. So what influences the choice of your two species. So in my case, historically, when I started this, I was young and poor, and so I chose the two species where the lasers are the cheapest, which is rubidium and cesium. Today, maybe I would choose, make a different choice. I guess I can convince people to give me more money, and then you might think about the dipole, the size of the dipole, for example. And I have a colleague, actually, Phil, who I persuaded to start work on a silver experiment, again following one of Mikhail's proposals, that where the
I was
dipole will be
about to say that
huge.
we have another one of these here. Yeah.
Yeah. So I think there are many reasons for picking the type of experiment, but I'm very happy that rubidium cesium works so well. So I think we will stick with it for a while yet. Yeah.
Thanks for that very honest answer. I think that there's a lot of space for such answers that, well, is not getting filled because it doesn't sound
Yeah.
sexy, but that's the truth. Okay, another question, and I see that we are closing to the end. Could you please restate the argument why the sticky collisions are prevalent in this case if, from what I understand, the presence of laser in the creation of rubidium-cesium complexes shows in these bottles might be broken after all?
So the issue is that this complex, so the collision complex should form. Okay, I think that's understood. And in fact, our measurement shows that the collision complex is forming. The fact that when we do this experiment partially in the dark, we're able to measure a lifetime associated with the collision complex, shows that collision complex actually forms. And then really it's just that the laser, again, if you take a diatomic molecule, there are so many transitions, right? This is now a complex, a collision complex, which has 4 atoms in it. And somehow that amplifies the number of transitions. And so it's basically impossible to avoid being close to a transition. And so the light of the trap actually just excites the complex almost as soon as it's formed. And then that excitation then decays somewhere. And where it decays is almost certainly not where it started because of the selection rules or lack of selection rules in the molecule. Yeah.
Okay, thank you. Michał, would you like to have one last question, or I know you have one prepared?
I have many, but if you have time, so maybe very brief, because now you have, let's say, 95% fidelity or contrast for your molecules entangling gates. So what are the prospects for getting 99% soon for molecular gates and scaling into larger number of molecules to build the quantum processor, not to call it quantum computer?
I think the pushing to 0.99 is actually quite straightforward, I think. So what currently limits us is we have a little bit of interaction noise, which is effectively the molecule, the tweezers are moving, or the molecules are hot. Okay. And I have to say the way we made this experiment was very much cobbled together. So the dirty secret was because we're using an AOD to make the 2 traps, an AOD relies on different frequencies to give different trap positions. But different frequencies breaks the magic condition. And so in order to make the 2 tweezers magic, we actually chop them on and off. So we chop the intensity on and off. And when it's on, we change the frequency slightly. And that way the 2 tweezers can be magic at the same frequency. So really we were doing this measurement not in 2 tweezers, static tweezers. We were doing it in 2 time modulated tweezers. So it's like the worst possible way to do the entanglement. So I think, and we know how to sort this out. And there are many ways we can sort this out. And that should push the entanglement up, the fidelity. And there's also more sophisticated gate operations. Scalability, that's a different question and perhaps a more challenging topic. But we're working on it. Actually, at the moment, we're putting in a lattice. So why is our molecule formation low? It's because of the axial cooling. So we have to do this Raman sideband cooling, and that's quite difficult in the weak direction of the tweezer. And so we've added a lattice that will allow us to have higher frequencies there. It's also a lattice that allows us to put the rubidium atom and the cesium atom in the same tweezer by separating them with the lattice. I think that will lead to better molecule formation probabilities. And in terms of numbers of traps, that's just laser power, so we're working on that. The real game changer would be direct detection of the ground state molecule, and that's where the Rydberg atom comes in. I haven't talked about that, but you know about our work. You know, we want to use a Rydberg atom to detect a ground state molecule, and then we can do rearrangement. And then we can start the company and make a molecular quantum computer.
Great.
I can't even say it without a smile on my face.
That sounds amazing. Okay, since we are 5 minutes past 4, I think it's time to conclude today's lecture. Let's thank all again Simon for his magnificent lecture this week.